Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the previous lectures, we have looked at how the structure can be excited using impact hammer and how the force can be measured. We also looked at how the resulting response can be measured. So once the force and response signals have been measured, then we need to find a frequency response function. So in lecture today, we are going to look at some estimates of frequency response functions, and also we are going to look at what is coherence function. So therefore the topic today is FRF estimates and coherence function. So a brief outline of the lecture is as follows. First we will define the FRF estimates H1 and H2. Then we are going to see that how H1 and H2 can be found by spectrum averaging. Then we are going to see that what is the effect of noise in the input and output on the estimates H1 and H2, and then at the end we are going to talk about what is coherence function. So therefore first of all we are going to talk about FRF estimates. So we have now the force and the response signals, right. So we have the force signal which is f of t, and then we have the measured response signal represented by x of t, and then taking their Fourier transform, we obtain their frequency domain representation. So f of omega is the frequency domain representation of the f of t, and then we have x of omega, frequency domain representation of x of t. So this we can obtain using discrete Fourier transform, right. So then we also defined the frequency response function, right, FRF, and let us represent frequency response function by general notation h of omega. So h of omega, and this is nothing but the ratio of the response Fourier spectrum and the force Fourier spectrum. So x of omega divided by f of omega. Now in practice often there is some measurement noise in the measured signals. So how can we reduce the effect of measurement noise in the FRF estimate? So some estimates of frequency response functions have been defined or developed which aim at reducing the effect of measurement noise on the FRF estimates, and two of such estimates H1 and H2 we are going to define, and we are going to also see that what is the effect of noise on these estimates. So let us first of all define the estimate H1. So estimate H1. So we know that the frequency response function is h of omega is equal to x of omega upon f of omega, right. Let us divide and multiply the right hand side by f star omega. And what is f star omega? F star omega is basically complex conjugate of f of omega, right. So we should note that the x of omega and f of omega, they are complex quantities, right. They have main root as well as phase, and f star omega is nothing but complex conjugate of f of omega. So by multiplying and dividing by f star omega, we basically get f star omega x of omega divided by f star omega f of omega. And now we represent this numerator by g f x omega and denominator by g f f omega. right. And what is GFX and GFF? Now what are GFX and GFF? GFF is called auto spectrum of force, okay, it is auto spectrum of force signal, okay, and it is nothing but the square of the magnitude of the spectrum f of omega. It is nothing but square of the magnitude of f of omega, right, and this has only magnitude, it does not have any phase, right. So auto spectrum does not have phase information. So f of omega has some phase, however auto spectrum of f of omega does not have phase, it just has magnitude. So it is also called as power spectrum, also called as power spectrum, because it gives the power of the signal at each frequency. GFX omega is called cross spectrum between f and x, okay, it is a cross spectrum between force and x, and cross spectrum has both magnitude and phase, okay, has both magnitude and phase, and the phase of the cross spectrum is the relative phase between f and x, okay, the phase is nothing but relative phase between f and x, right. So therefore this ratio GFX omega upon GFF omega is also equal to frequency response function, and this frequency response function estimate is referred as H1, okay. So how one can find the frequency response function estimate H1? From the measured signals x of t and f of t, we first find their frequency domain representation, their Fourier spectrum, and then from the Fourier spectrum we calculate the auto spectrum and cross spectrum GFF and GFX, and then we take the ratio of the two to find the FRF estimate H1. Let us look at another estimate H2. So again writing the expression for h of omega, which is ratio of x of omega and f of omega, and now if we divide and multiply, right, if we divide and multiply by this time x star omega, okay, then we get x star omega into x of omega divided by x star omega into f of omega. So x star omega again is the complex conjugate of x of omega, and then this quantity x star omega x omega, you know, is nothing but the auto spectrum of response x, and x star omega f of omega is nothing but a cross spectrum between x and f, right. So this estimate is basically called H2 estimate, H2 omega, correct, and we should note that here GXX omega is nothing but auto spectrum of x, and GXF is nothing but the cross spectrum between x and f, right. So all the auto spectrums are magnitude spectrums, they do not have any phase information, and cross spectrums have magnitude as well as phase, the relative phase between the two signals in question. So this is estimate H2. So if there is no noise, right, in the measured signals, then the estimate H1, H2 and H of omega, they all will be equal because they are all mathematically equivalent. So, they are supposed to be equal when there is no noise. Then the question arises, because in practice there is some noise, then how the effect of noise can be reduced. So, for that purpose now these H1, H2 they are obtained using spectrum averaging. So, let us see what is spectrum averaging. Spectrum averaging. So, for spectrum averaging we perform the test at a test point repeatedly, right. We take the measurements repeatedly at a particular point. So, for example, if we are doing a hammer test, then we can apply the impact at a one point and then measure the response and force, correct. And based on that force and response we can find the required auto and cross spectrums. Then we again apply the impact at the same point, right. After the structure has come to rest, we again apply the impact and then we again measure the response and force and again find the auto and cross spectrums. So, in this manner, let us say if we perform that apply impacts m number of times, right, then we get basically m number of cross spectrums and m number of auto spectrums, and then we can take the average of all these auto and cross spectrums to find an average estimate of auto and cross spectrums. And if the noise in the two signals, if it is random, right, noise and it is uncorrelated with the force and the response signals, then because of the averaging the noise in the estimate FRF will reduce, right, noise in the auto and cross spectrums will reduce, right. So, this is basically the idea of spectrum averaging. So, let us say we have taken m number of averages. So, let us say m represents the number of averages. So, then now we find the auto and cross spectrums based on averages of the different auto and cross spectrums corresponding to different measurements. So, therefore, we write down say auto spectrum of X, we write as 1 by m with then we have X star omega, and let us say this corresponds to the jth measurement, and then we have X j omega, right, and this j varies from 1 to m, correct. So, for each j we find auto spectrum and then we sum all these auto spectrums and then divide by m. So, that gives us the average estimate or average value of the auto spectrum. Similarly, if we have the auto spectrum of the force can be obtained similarly by summing all the auto spectrums corresponding to different measurements. So, f j star omega f j omega, right, and then we can find a cross spectrum. So, let us say g f x omega as 1 by m, j varying from 1 to m, right, and then we have f j star omega into x j omega. And we should also note that g x f omega is nothing but complex conjugate of g f x, okay. So, they are related by complex conjugate relationship. So, in this way by spectrum averaging we obtained the average estimates of auto and cross spectrums, and then the estimates H1 H2 simply are given by H1 omega is nothing but g f x omega divided by g f f omega, while H2 omega is nothing but g x x omega divided by g x f omega. So, in this way we can obtain the estimates H1 H2 by spectrum averaging. So, if spectrum averaging is done, then we expect that the H1 H2 will be closer to the true FRF. So, let us now try to see that if there is noise in the input and output, how these estimates H1 H2 are affected, okay. So, now we are going to analyze the effect of noise on H1 and H2. okay. And let us assume that H true is the true estimate of the FRM, and this true estimate is unknown, right? We do not know what this true estimate is, and we are trying to find some estimate of H true using H1 and H2 based on the measured signals. So, this H true is, let us say, it is an unknown true estimate of the FRM, and let us first of all assume that there is noise in the output only, okay. So, let us say there is noise in the output, that is the response. So, there is noise in the response, and let us say there is no noise in the applied force, right. So, let us depict this situation by a figure. So, we have this say system like this or structure, and then this is subjected to some excitation f of t, which results into response x of t, right, and there is some noise, uncorrelated random noise in the response. So, it means some noise gets added to this response. Let us call that noise as n of t, and then the what we measure is the noisy signal, let us represent it by x bar t. So, x bar t is the measured signal. So, this is measured response signal, this is uncorrelated random noise, and f of t is the measured false signal. So, n of t is uncorrelated random noise, which means that it is not correlated with either x or f, it is uncorrelated with that. And how this noise can actually creep into the system? One possibility is that if there are some extraneous excitations acting on the structure in addition to the force we are applying, okay. So, we may have, so n of t maybe due to some extraneous excitation of the structure, for example due to some ambient loading, right. So, say due to some ambient sources, okay. This could be one reason. So, these extraneous excitation will also excite the structure and result into some response, right, in addition to the response generated by the applied force. And this extraneous excitation in general would be uncorrelated with the applied force, and therefore, the corresponding response that is generated, that also will be basically uncorrelated, and therefore, that would basically appear like an uncorrelated random noise in the output signal. In addition, there may be some random noise, measurement noise due to instrumentation, due to electrical circuitry and so on, right. So, there may be some random measurement noise. Therefore, we can say that we have signal x bar t, which is the measured response signal, it is equal to x of t plus n of t. And if you take Fourier transform of this, what we get, x bar omega is equal to x of omega plus n of omega, right, that is what we get. And let us now try to determine what is the effect of this noise on the estimates H1 and H2. So, let us first of all determine the effect on H1, right, and H1 now can be written as H1 omega will be equal to now the G F, and now we have x bar, right, because now the measured response is x bar, not x. So omega divided by g, the measured force is F itself, so g f f omega. So now how g f x is affected by noise? So we can write g f x as 1 by m, j varying from 1 to m, then we have f star j, right. So let us do not write this omega into bracket. So then we get f j star into x bar j, right, and then we have this we can write as m j m f j star into x j plus n j, right, and that gives 1 upon m f j x star f j star x j plus f j star n j, right. So the first quantity can be written as the cross spectrum between f and x, right, and the second quantity is nothing but the cross spectrum between the force F and the random uncorrelated noise n. Now here this GFN will be approximately 0, right, it will tend to 0 for large number of averages, because the noise signal is uncorrelated with the force signal, okay, and therefore GFX bar omega will be equal to GFX, correct, and now GFF is unaffected by noise because there is no noise in the force signal, and therefore H1 omega turns out to be equal to GFX omega upon GFF omega, and this is nothing but the true FRF. So this is equal to the true FRF, because this is dependent on the true force and true response. So H1 therefore is unaffected by noise in the output, right. So that's therefore that is the advantage of spectrum averaging, that noise in the output can be effect of noise can be eliminated in the FRF by estimating the FRF H1. Let us look at what is the effect on H2, right. So now H2 is given by G x bar omega, right, divided by G x bar f, right, and let us now look at what is G x bar omega. That is nothing but 1 by m, j varying from 1 to m, then we have x bar j star omega, x bar j omega, okay, and then this can be written as 1 by m, j is equal to 1 to m, x j plus n j, right, star into x j plus n j. So therefore this we can now write as if you multiply the terms then and then take the average, then we can write this as g x x plus g x n plus g n x plus g n n, right. Now here the noise n is uncorrelated with the response x, right, and therefore Gxn and Gnx will tend to 0 for large number of averages. Gnn is the auto spectrum of the noise signal, okay, and so it is the magnitude of the square of the magnitude of the noise signal Fourier spectrum. This would be non-zero, and that is why we end up with Gx bar x bar being equal to Gxx plus Gnn, isn't it. So therefore, we see that the auto spectrum of the response signal is affected by noise, right. And what about GFF? We can write here no, so sorry, Gx bar f. Now Gx bar f is the cross spectrum, right, of the measured signal x and the force signal, and this is nothing but the complex conjugate of the Gfx bar, right. And we already have determined that Gfx bar is essentially equal to Gfx. So, this is equal to complex conjugate of Gfx, and complex conjugate of Gfx is equal to Gxf, isn't it. So, we see that the Gx bar f, which is the cross spectrum between x and f, it is unaffected by noise in the output, correct. And therefore, now we can say that here the Gx bar x bar is equal to, I think let us write it on the next page. So, we can write down H2 omega as Gx bar x bar omega upon Gx bar f omega, and we just saw that Gx bar x bar omega is Gxx plus Gnn, right, and Gx bar omega f is Gxf, isn't it, and then Gxx upon Gxf plus Gnn upon Gxf, right. So, Gxx upon Gxf is nothing but the true frequency response function, okay, plus Gnn upon Gxf. So, we see that H2 omega is not equal to H true, right. In fact, H2 omega is always more than or equal to H true. This we can see from this equation, right. From this equation we can see that. So, in the numerator we have the auto spectrum, sum of the auto spectrum of the response signal and the noise signal, and Gnn is always positive, okay, because it is square of the magnitude. So, it is always positive. So, it means the numerator will always increase because of the non-zero noise in the output, and because of this the H2 omega will always be either more than or equal to H3 omega. So, if there is no noise, H2 is equal to H2, but if there is noise, H2 will be more than H2, okay. So, therefore, if there is noise in the output, the H1 estimate is the preferred estimate to eliminate the effect of noise on the FRF, okay. Let us see what is the effect of noise if in the input on these estimates, okay. So, effect of noise in the input. So, therefore, now what we have got? We have this system like this, and then we have this force that is being applied, that is f of t, and that causes the response x of t. However, the measured force has some noise. So, it means that we have some noise here, let us say, and that is represented by noise by q of t, and this is the f bar t, which is the measured force. Okay, and q of t is uncorrelated random noise, right, in the measured force, and x of t is the measured response. So, the measured response does not have any noise, however, the measured force has some uncorrelated random noise, right, and q of t can be due to some random noise in the force signal, right, which may be because of some noise in the instrument or some random noise that is generally present in the measured signals, right. So, random measurement noise. And we have got therefore f bar t is equal to f of t plus qt. So, if we take Fourier transform of this equation, then we get f bar omega is equal to f of omega plus q of omega. Let us now try to determine the effect of noise in the input on the H1 and H2. So, let us first of all look at effect on H1, and we know that H1 omega is g f x g f bar x omega, because now f bar is the measured force, and then we have g f bar omega. So, now g f bar x is given by g f bar x 1 upon m, j is equal to 1 to m, we have then f bar star j into x j, right, and then this would be f j plus q j star into x j, right, and then this is g f x plus g q x. And because the noise q of t, it is uncorrelated with the response x, and that is why g q x would tend to 0 for large number of averages m, and therefore g f bar x would be essentially equal to g f x, it will be approximately equal to g f x. And then similarly we can easily show that g f bar omega, proceeding as we did for g x bar omega earlier, it can be shown that this will be equal to g f f plus g q q, right. So, the auto spectrum of the force would contain the effect of noise, right. So, it will be equal to the auto spectrum of the actual force and the auto spectrum of the noise in the force. So, what is the effect of in noise in the input on H1? So, therefore, H1 will be therefore equal to g f x divided by g f f plus g q q, isn't it? And this we can also write as g f x upon g f f and g f f upon g f f plus g q q, right. So, dividing and multiplying by g f f, and what we note that in the this quantity is nothing but h true, this coefficient g f x upon g f f is basically h true, and this term in the bracket, okay. So, let us, if we represent it by some factor, let us say beta, this term in the bracket, this factor beta is always less than 1, because the GFF and GQQ, they are positive quantities, right. So, here the numerator is always less than the denominator, okay, and that is why beta is always less than 1, okay. So, this is H1 omega. So, from here therefore, what we conclude that, let me write here, that the factor beta is always less than or equal to 1, right, and that is why H1 omega is always less than or equal to H true. So, if there is no noise, H1 is equal to H true, but if there is noise in the input, then H1 will be always less than H true. So, therefore, noise in the input affects the estimate H1. So, it deviates from the true estimate, right. So, there is some error in the estimate H1 if there is noise in the input. Let us see what is the effect on H2. So, H2 omega is given by G x x omega upon G x f bar omega, right. So, x is the measured force and f bar is the so x is the measured response and f bar is the measured force. Now, so we have seen that G x f bar will be basically equal to the complex conjugate of G f bar x, and just now we saw that G f bar x is nothing but G f x, right, and the complex conjugate of G f x is nothing but G x f, isn't it. So, therefore, we see that G x f bar is equal to G x f, which is the correct value of the cross spectrum, correct, and therefore, H 2 omega will be basically G x x omega divided by G x f omega, and this is nothing but the true frequency response function. So, we see that here the noise in the input does not affect the estimate H1, okay, it is equal to the true estimate. So, therefore, H2 is unaffected by noise in the input, is unaffected by noise in the input, and therefore, whenever there is noise in the input is expected, H2 estimate should be preferred. Now, let us take the situation where the noise exists in both input and output, right. So, noise in input and output. Let us try to depict this situation through a simple figure. So, we have this system here, this is the applied force f of t, and there is some noise in the measured force. Let that noise be q of t, and let us say this is the measured force. Similarly, let the response is x of t, and then there is some noise in the measured response. Let that noise be n of t, and let x bar t be the measured response. Right. So, q of t and n of t are the uncorrelated random noise in the input and output respectively. So, let us determine the effect on H1. So, H1 is given now by G f bar x bar omega divided by G f bar omega. So, now we can analyze this case similar to what the analysis we did when the noise existed only in the input and output. G f bar x bar should be equal to G f x, right. So, G f bar x bar should be equal to G f x, and why that is so? Because the noise q and n in the input and output, they are not correlated with either f or x, and they are also not correlated with each other, and that is why when we take the averages, the all the cross spectrums between q and n, q and f, q and x, n and f and n and x, all those cross spectrums would be 0, and that is why we would have only the the non-zero cross spectrum between the force and the response. And similarly, G f bar would be affected by auto spectrum of the noise q, and then we can write down that as G f f plus G q q, right. So, that is H1, and then what we see that this therefore is affected. So, this is equal to, as we did before, we can multiply by GFF and divide by GFF, which gives us GFF upon GFF plus GQQ, right, which shows that H1 omega is either less than or equal to H2, right, because this quantity is nothing but H2, and this factor is always less than or equal to 1, the beta factor we called earlier. Similarly, let us now determine what is the effect on H2. So, H2 omega is equal to G x bar omega divided by G x bar f bar omega, isn't it? And then now G x bar omega would be equal to G x x plus auto spectrum of the noise in the response, that is G n n, and then G x bar f bar again would be G x f. So, this can be written as G x x upon G x f plus G n n upon G x f is H true plus G n n upon G x f. So, therefore, here H2 omega it will be more than or equal to H true, right. So, therefore, what is the conclusion? That the estimates H1 and H2 now both will be affected by noise, okay. They both will be affected by noise because noise exists in the input as well as output. However, these H1 H2 they provide lower and upper bound on the true FRF. So, we see that H1 omega is always less than or equal to H true, right, and H2 omega is more than or equal to H true. They provide the lower and upper bounds. So, H1 omega is the lower bound and H2 omega is the upper bound on the FRF on H true, right. So in many situations some extraneous excitation might be present, right. So, we might not know that, but it might be present, some ambient excitation or ambient loading, okay. So, in such cases therefore, then H1 can be used as the estimate to find the frequency response function. So, if there is measurement noise which cannot be completely avoided in practice, okay, there will be some small measurement noise which might always be present. So, is it possible to assess the quality of the measured FRF, right. So, can we know that the FRF we have measured, how much it is likely to be correct, right. So, if index based on coherence function has been defined which allows us to assess the quality of the measured FRF. So, let us talk about coherence function now. Okay. So, the quality of the measured FRF can be assessed using coherence function. So, the coherence function is given by the ratio of H1 and H2. It is given by the ratio of H1 and H2 because H1 and H2 they form the lower and upper bound. So, this ratio can serve as the index of the noise in the FRF, because if there is no noise then H1 and H2 are equal to the true FRF, correct. So, we know that if there is no noise, right, then H1 is equal to H2 is equal to H true. So, both of them give the true estimates. So, in that case the coherence function, right, it will be equal to 1, right. So, therefore, coherence equal to 1 represents no noise in the FRF, but if there is noise, then we saw that H1 will be less than H2 and H2 will be more than H2, and because of this the coherence will be less than 1. Okay. So, that therefore, coherence less than 1 is an indicator of noise in the FRF. Okay. So, the coherence is always between 1 and 0, right. So, this coherence essentially captures the degree of linear relationship between the output and input. Okay. So, the coherence function quantifies the degree of linear relationship between the output and the input. So, if the output and input are perfectly linearly related, then the coherence will be 1. Okay. But if there is noise, then what happens, this linear relationship is broken down, and the extent to which it is broken down depends on the amount of noise, right. So, higher the noise, higher is the discrepancy, or higher is the deviation from the linear relationship, and then higher is the drop in the coherence. The other reason for which coherence can be less than 1 could be because of any non-linearity which might be present in the system or the structure. So, even if there is no noise, any non-linearity in the system may also make the coherence less than 1, okay, because it captures the linear relationship. So, non-linearity causes the output to be non-linearly related with the input, right. So, therefore, coherence function will be less than 1 when there is any non-linearity in the system. Okay. So, thus both noise in the measurement and any non-linearity makes coherence to be less than 1. Okay. So, in practice, for example, if the modal test is being conducted with a small amount of force, which is generally the case, then the non-linearities, even if they are present, will not be excited. Okay. So, in such cases, the any drop in the coherence will be equally due to the noise in the measured signals, right, and the noise in the FRF will affect the coherence function. And therefore, the coherence function can be used to assess the quality of the measured FRF and to determine that how much the FRF is being affected by noise in the measured signals. There are few more checks that can be done to assess the quality of the measured FRF. One of such consideration is reciprocity. Right. So, we know that for a linear system, due to reciprocity, we have studied earlier that alpha jk FRF, right, the FRF at due to response at the jth degree of freedom and the excitation applied at the kth degree of freedom is equal to FRF alpha kj, right, which is the FRF based on the response at the kth degree of freedom and the excitation at the jth degree of freedom. So, it means that if we swap the excitation and response DOF, right, if they are interchanged, then the for linear system the FRF should remain unchanged, we should get the same FRF. So, this is one way we can check whether the way we are measuring the FRF, right, whether it is, and the FRF we are measuring, whether it is, to what extent it is correct, right. So, the we can measure alpha JK FRF, and then we should interchange the response and excitation DOFs, and again measure the FRF, which will give us the alpha KJ, and then we can overlay these two FRFs, and any discrepancies between the two indicate any inconsistencies which are there in the measurement, right. So, this is one check that can be done to check the validity of the measured FRF. So, another check that can be done is repeatability check. This basically means that if we repeat the FRF measurement, then ideally we should get the same FRF. There may be small changes due to changes in the noise from measurement to measurement, but by and large we should be able to get a similar measurement, right, because FRF is the system property. So, the system property should not change, right, if everything else remains constant. So, these are the checks that can be done to assess the quality of the measured FRFs. So, in this way today we looked at the FRF estimates, and we looked at the estimates H1 and H2 and how they are affected by noise in the input and output, right, and we also defined coherence function which can be used to assess the quality of measured FRF. So, now we stop here. Thank you.